Okay, I hope everybody's doing all right today. We are going to go ahead and start the next section. Just a few things before we go ahead and get started. Don't forget the big item next week, right before we get out for Thanksgiving break, is the test on Thursday, the 15th. Look for that to have, law of sines, law of cosines. Be familiar with those area formulas we were looking at for oblique triangles. And also the current homework assignment you're working on, that material is going to be on the test as well, graphing sine and cosine. Speaking of, when's the homework due? It is due Monday, okay. And on the test itself, don't forget you can use a note card. It's got to be a 3x5 note card. It can't be a 3x5 piece of paper that you either ripped or cut out. It's got to be a note card. You can write on the front. You can write on the back. You just can't add anything to it to give yourself extra space, like a fold out or something. Okay, just the 3x5 card. Now, the reason I'm allowing you to use the 3x5 card is, you remember the ambiguous case, the side-side angle scenario where we had that table with the acute, the obtuse in the bottom row, 0 triangles, 1 triangle, or 2. I did put problems on there specifically related to that. So somewhere on that card, you definitely want to have that table. Okay, either, copy it, shrink it down, or write it out, whatever you need to do. But, okay, definitely have that on there. All right. Well, before we get started, is there any questions? Anything we need to talk about? Someone at the door. Okay, let's put that in the tray, sir. All right, well, let's go ahead. Now, this is just kind of a supplement to the lesson we finished up yesterday. Bless you, and it's more so for the people who are going to be moving ahead to calculus. You're going to be hearing these vocabulary words, and I just want to make sure that you're familiar with them when you get there. So any transformation of a sine function is what we're going to call a sinusoid. Now, all 5 of the other trig functions we're looking at, cosine, tangent, secant, cosecant, and cotangent, in some way, all of them can be related back to sine. So we can refer to all of those as sinusoidal functions, okay, any transformation of those. We've been talking about the general forms. So a sine of bx plus c plus d. And for my resource, it had all these as capital letters, but if you see them as lowercase, that doesn't change anything. The leading coefficient a will help you with the amplitude. Remember the absolute value of a. B is the coefficient of x. He's going to help you with the period, 2 pi divided by b. C is what we add or subtract to x. That's going to help you with your phase shift. We take c divided by b. And then D is your vertical shift. That's going to move my midline up and down. And you'll know if you're affecting this vertically or horizontally, be looking for the parentheses. Okay. But let's go ahead and take a look at the other one I want to today. The frequency of a sinusoidal function is the number of cycles the function completes in a 1-unit interval. Now, it's really easy to find. The frequency is just the reciprocal of the period. Now, we know the formula as 2 pi over, that capital B. Don't worry about the fact that this one has a lowercase b. Like I said, that doesn't change anything. Now, typically, you may see it in some resources and some other ones as having an absolute value around it. The only time you have to worry about that is if b is negative. We'll always take the positive version of b when we're looking for the period and the frequency. Okay, but you just go ahead and flip it. So let me go ahead and show you an example to hopefully make this a little more clear. This right here is the graph of sine. What's the period for sine? 2 pi. Now, 2 pi is the number of radians needed before the graph will repeat again. What repeats is what we call a cycle. Okay, so let's say that this period here is 2 pi radians, and I'm interested in the frequency. Well, what's the reciprocal of 2 pi? It would just be 1 over 2 pi. Yeah. So what this is telling me is that I should see one cycle, one repeating pattern in a 2 pi length. So if you go ahead and take a look, see here's 0, here's 2 pi, and I see that one familiar shape for sine in that interval. Okay. Let me go ahead and give you another one. This one's already been graphed for us. Sine of 3x. Is this going to be a vertical or a horizontal transformation? Okay, horizontal. Okay, it's definitely affecting the x. It's inside those parentheses. It's inside the trig function. Would everybody agree that the value of b is 3? Remember, that's the coefficient of your x, right? Okay. So what kind of transformation is this? Is it a phase shift? Is it a reflection? Is it a dilation? It's dilation. Now, how do we know it's a dilation and nothing else? What operation am I using? We're multiplying. Okay. So we're multiplying. If we're adding or subtracting, then it would be a phase shift. A negative is a reflection. But what would the period for this graph be? 2 pi over 3. That's it. Okay. So the period. There we go. 2 pi over 3. Okay, so it's going to take 2 pi over 3 radians for it to go ahead and repeat over and over, right? But let's go ahead and find the frequency. The frequency is always the reciprocal of the period. So what's the reciprocal of 2 pi over 3? It's 3 over 2 pi. So what this is telling me is that I should see 3 repeating patterns, 3 cycles in a 2 pi interval. Well, let's see if that's true. I'm going to start here. There's 0. Here's 2 pi right here. Okay. Well, let's go ahead and see. Here's 1. Here's 2. There's 3. Okay. That's all the frequency is. The number of cycles you're going to have in a given radian interval. Okay. Any questions on that? Okay. Pretty easy? Good. Okay, well, let's go ahead and take a look at this now. We're going to go ahead and start getting into the other trig functions, but today we're only going to look at tangent. We'll look at cotangent and hopefully the other ones on Monday. But it says the graphs of tangent, cotangent, secant, and cosecant functions are also periodic. So at some point, they're going to go ahead and start repeating as well. Okay, but tangent and cotangent will have a shorter cycle or period than the other 4 functions. Okay, so we need to go ahead and define that. So instead of going through this whole thing, let's just go ahead and state the period of tangent is going to be pi. Okay, so every pi units, the graph should be repeating itself over and over again. Now, I'm going to go ahead and start with the ratio, and then we'll talk about the graph, and then we'll do just like we did with sine and cosine. I'll relate it back to the unit circle so you can see why we have those particular values. So let's start with tangent. Okay. Now imagine you're just evaluating a measure on a unit circle, just like your happy minutes. What is tangent's ratio? Oh, y over x, right? Okay, so y over x. But we know by now y represents what trig function? Sine. X represents cosine. So using that ratio, I can rewrite tangent in terms of sine and cosine. You remember how I said that every graph somehow is going to relate back to sine, which is why we can call them sinusoidal? But there's a reason why I'm doing this. I'm going to focus on cosine, specifically because he's in the denominator. Okay, so I'm going to go ahead and graph cosine very quickly. You'll want to do this a lot because you'll want to go ahead and erase him. But where does sine begin? Cosine, sorry. Cosine begins at 1. He has a maximum. Then what's the pattern on the critical values? We have a 0, then a minimum, 0, maximum, and then we'll go in the other direction as well. So we have a 0, minimum, 0, maximum. Okay. So here's cosine right here. So just bear with me for a few more seconds. Okay, why are we drawing cosine if we're trying to figure out what tangent looks like? Okay, well, think about this graph right here. We rewrote tangent in terms of sine over cosine, right? When you have a fraction, what is the one thing you cannot divide by? You cannot divide by 0. So it's really important to know where cosine is 0. Wherever cosine touches the x-axis, that's where tangent is going to be undefined because we can't divide by 0. What do you think I'm going to have at that location? Think back to your rational functions. We're going to have an asymptote. Every place that cosine touches, negative 3 pi over 2, negative pi over 2, pi over 2, 3 pi over 2, and that pattern is just going to continue over and over again. Remember, we just said that how wide is tangent? What's its period? It's pi. Well, how far are those asymptotes from each other? Yeah, it's only pi radians. So now I'm going to go back and I'm going to go ahead and erase cosine because he helped me out. And the nice thing about these graphs, they're always symmetric. There's always patterns here that I can use. The x-intercept is always going to be halfway between these asymptotes. So what's halfway between negative and positive pi over 2? What's halfway between those two? 0. So that's where my first intercept is going to be. And then the midpoint for each of the next set of asymptotes is going to be an x-intercept as well. So one here, one here. Now let's focus on the one about the origin. If you're looking at tangent's parent, which we are right here, the point pi over 4, 1, and the point negative pi over 4, negative 1, will always be on the graph. So that gives me 3 points. This is what tangent looks like. Okay. Now remember, I said it's all about patterns, right? So I could follow that same pattern between every set of asymptotes that I have. For this other intercept here at pi, I can go 1 to the right and 1 up, 1 to the left and 1 down. So I can draw the exact same graph. Over here at negative pi, 1 to the right, 1 up, 1 to the left, 1 down. There we go. And this is just going to repeat over and over again. Okay. Now, you remember how sine and cosine have those critical values? Like, for example, sine is the 0, maximum 0, minimum 0. Well, all these other graphs are going to follow the same pattern. He has his own critical values as well. But we're just looking at one period. So I'm going to start with an asymptote. So we're going to identify that as just a no solution symbol. Okay. And then look at the y values as we go through one period. See, I have a negative 1. Then I have a 0. What's next? I got a positive 1. And then what do we get back to? We get back to no solution because we're now at the next asymptote. Okay, so tangent is going to have critical values just like the other ones, and it's going to be really useful to us when we go ahead and start transforming him. Okay, and at this point, I need to be really careful because my tan line is showing. My tan line. Come on, that was a good one. Okay. Moving on. All right, well, why do we have those points that we do on tangent? Well, I'm going to go back to the unit circle, and I'm again going to go ahead and show you how this works. But you remember between these 5 critical points, whether sine, cosine, tangent now, how many congruent distances are we looking for? We always have 4, right? We always have 4 congruent horizontal distances in any given period. So here, we have 1, 2, 3, 4, just like we did before. Well, what are the increments that I have? What's a fourth of this period? Pi over 4, right? So that's what I'm going to be looking at when we get to the unit circle. Okay, so here's my unit circle. It's already filled in for me, everything I need. Let's start with tangent of 0. Okay. Tangent of 0 equals. Well, what does tangent want me to do at that location, though? What's his ratio again? He wants y over x, right? Okay. Well, what's this y value 0 divided by the x value 1? 0. So say this gives me the ordered pair 0, 0. Now, let's start rotating around in increments of pi over 4. So now I'm going to go to pi over 4. Tangent of pi over 4. Well, at pi over 4, I've got square root of 2 over 2, comma square root of 2 over 2. What's that y divided by that x? 1. So this is going to be pi over 4, 1. Hey, thank you. Looks like Miriam. Okay, I'm going to guess that's Miriam. Okay, it says immediately. All right, there you go, man. Uh-huh. Okay. Now, if I rotate pi over 4 more radians, well, now we're at pi over 2, right? Okay, so tangent of pi over 2, what's 1 divided by 0? Cannot be done. Remember, we can never divide by 0. Okay, now rotate another pi over 4 radians. Where am I? I'd be at 3 pi over 4. Okay. So tangent of 3 pi over 4. Well, I'm at this ordered pair. So what's that y value divided by that x value? -1. And let's go ahead and do one more. Okay, we rotate all the way to pi. Half a revolution. So tangent of pi, 0 divided by -1. 0. So this gives me 3 pi over 4, -1. This gives me the ordered pair pi 0. Okay. We'll go ahead and start looking at those ordered pairs on the graph that we just created. We start with 0, 0, which is what we have right here. Then didn't we have pi over 4, 1? Pi over 4 is right here, so that's that point. And then what happened when we got to pi over 2? No solution, because you can't divide by 0. Then we got to 3 pi over 4, where we had -1. And then what happened when we got to pi? We got to 0. Okay. So just like the other graphs, it's coming straight from the unit circle. It's just whatever that trig function wants you to do. Is everybody okay with how we get the graph? Any questions on that? Okay. Well, let's talk about the characteristics. Okay. Let's start with the easy one first. What would its range be? How tall is this guy? Yeah, he's definitely tall. He's not going to stop, right? So I'm going to say the range this time is negative to positive infinity. What's the y-intercept? 0, 0. Now remember, we're talking about the parent. Once you go ahead and start to transform these are no longer guaranteed. You have to be careful. All right. Now, let's go back to the domain. Will this go forever? Will he be infinitely wide? Can I continue to rotate around the unit circle? Yes, but we're not going to go ahead and say the domain is all reals because we have an infinite number of what? Asymptotes. So you remember like we did with sine and cosine for the intercepts, the maximums, and the minimums? We came up with a little expression to go ahead and identify those. We have to do the same thing here. So I'm going to go ahead and say x cannot equal. And let's go ahead and just start with pi over 2. Seems like a good asymptote. Really, you can start wherever you want. Okay. But how many radians would it take to get to the very next asymptote? Pi. Well, what about the next one? Next one. And it's just going to keep going, right? So what can I do with pi over 2 to help me identify those? Yeah, there you go. And you can use whatever variable you want. Wasn't this the class that was using n? Okay. So I'll go ahead and say plus pi n. You're just adding multiples of pi. We just have to make sure n is a what? Is an integer. And remember, the opposites are in the integers, so we can also have the subtraction there. Okay. Let's go ahead and look at the x-intercepts. The first x-intercept is at 0. Okay, so I'll go ahead and put 0 plus. Well, what's the next intercept after 0? Pi. What do you think the next one would be? 2 pi, because the period is pi, so it's going to repeat every pi radians, right? So what should I add to 0? Yeah, it's just like we did before. It's just going to be multiples of pi. Now, what is 0 plus pi n? It's just pi n, right? I just wanted to make sure, we had some kind of starting place. Again, n, it's got to be an integer. Okay. What kind of symmetry do you think it would be? Well, it says odd, but what is odd symmetry? If you rotated it how far? 180 degrees, yes. So this is symmetric with the origin. Okay. Excuse me. And then here's what's really nice. The asymptotes, don't we already have those? Yeah, remember, we had to identify where all the asymptotes were because they couldn't be part of our domain, but we actually want to list the asymptotes here. So I'm going to go ahead and say x equals pi over 2 plus pi n. Again, just making sure n belongs to the integers. Okay. Let's take a look at one problem, how to go ahead and transform these guys, and then we will go ahead and take some time in class to work on your assignment. Okay. So here's the one at the bottom I want to take a look at. -2 tangent of 1/2 x. Now, you remember that strategy I introduced you to in the last unit where you use the critical values, you create a compound inequality? We are doing the exact same thing when it comes to tangent, but you just have to be careful about what graph you're trying to sketch. If you're going to graph tangent or cotangent, you need to create your inequality, your compound inequality, using a consecutive set of asymptotes. What does that mean, consecutive? Yeah, they got to be in order, right? They got to follow one right after the other. Typically, what I like to go ahead and do is just use negative and positive pi over 2, but really when it comes down to it, as long as you have 2 consecutive asymptotes, you're good to go. All right, so I'm going to go ahead and set that up. Okay. All right, so I'm going to go ahead and say negative pi over 2 less than or equal to, and then less than or equal to pi over 2. Well, what am I going to put in the middle? Oh, not that. Remember, what were we doing with sine and cosine? We only put what was inside the function. So only those horizontal transformations. So here I want to put in x over 2. We'll take care of that -2 in just a second. How would I know he's vertical? Where is he? He's outside those parentheses, so I know he has to be vertical. Now, be careful on a couple of questions on your assignment. They did go ahead and pull out that common factor b to show you what the phase shift actually is. That's still considered a horizontal transformation. All right, so now how would I solve this for x? Yeah, just multiply through by 2. So it looks like I'm going to get negative pi less than or equal to x, which is less than or equal to pi. Okay, so there's my compound inequality. We're going to come back to him in just a second. Okay, now let's turn our attention to the critical values for one period of tangent. Remember, what were they that we listed a second ago? Okay, undefined, because we're going to start with an asymptote. Then we went -1, 0, 1, and undefined. Okay, that represented one period for tangent, from one asymptote to the other, right? Okay. Now, anything that's happening vertically, that's what's going to change these guys. The compound inequality takes care of the horizontal transformations. So what do you think I'm going to want to do to each and every one of these? What are my vertical transformations? What's outside my parentheses? Yeah. So I want to take each of those critical values and I just want to multiply it by what? -2. We're going to take care of both at the same time. Okay. So what do you think a -2 times undefined is? It's just undefined. There you go. It's going to stay exactly as is. What's -2 times -1? Okay, 2. -2 times 0. Okay. And is everybody seeing where I'm getting these values from? It's the same process you're going to be using for sine and cosine on your assignment. What's the next one? -2, and we finish up with what? Undefined. Okay. So these are what my critical values should be after these transformations. Okay. Now, just like we've done before, the lower boundary, I'm going to pair that with the very first value there. Where am I going to put the upper boundary pi? Yeah, we always put the lower boundary at the very beginning. We put the upper boundary at the very end. Okay? And now, we always want to divide this distance by what? Always by 4. So can anybody tell me, what am I going to be adding over and over again to fill in those missing blanks? Okay, what's that, Jacob? Pi over 4? Very close. Now think about it. How far a distance is it from negative to positive pi? That's 2 pi, right? And then we want to divide that by 4. So I actually need to go ahead and add pi over 2. Okay. So what is negative pi plus pi over 2? Negative pi over 2. Now what's negative pi over 2 plus pi over 2? 0. 0 plus pi over 2. And does it work out again? What's pi over 2 plus pi over 2? Pi. Remember, this is exactly what we've done with sine and cosine. But you'll notice this gives me 3 ordered pairs on 1 period of tangent. How do I graph negative pi undefined? That's where your asymptote has to be. So I know that at negative pi, there has to be an asymptote right there. I know that at positive pi, there's another asymptote right here. And I know I have negative pi over 2, 2. So left pi over 2, up 2. We have the point 0, 0. And then pi over 2, negative 2. There you go. And now, once I have a period, I can just repeat that over and over and over again. Let's see, from an asymptote, we would need to go 1, 2, 3, 4 to get to the next intercept. So from this asymptote, 1, 2, 3, 4, and I know that there's a point 2 left and 1 up on this grid. So there would be probably about here. There you go. You just repeat the pattern over and over again. And there you go, there's tangent. Okay. But wait a minute, I got a question because I confuse easily. We were just looking at tangent a second ago, right? Doesn't tangent look like this? What happened? The negative caused him to flip, right? Also, look back at the original. Okay. What's his period? His period is pi, right? Well, this graph to me looks like he's double the width he was originally. Is that what we would expect to happen? Why? Yeah. You remember when you're looking at the dilation, whatever you multiply x by, you have to what? Oh, not the opposite. You do the opposite if you add or subtract. You have to take the reciprocal. So the reciprocal of 1/2 is 2. So it makes sense this guy is twice as wide as he was originally. Okay. And we also reflected him. Is everybody okay with that? Anybody have any questions on where anything came from? Okay. Then that is all I had for today. I'd say we got about, what, 12 minutes left? Okay, so that's a decent amount of time. So I would encourage you, go ahead and look at your homework. It is due on Monday. Now, graphing sine and cosine will be on your test, but tangent and the others will not. Yes. Yeah, sure, pass it over there. Okay. All right. Well, good, good, good. In fact, was anybody having any trouble with the homework? Zach? Oh, you haven't even started it yet? Perfect opportunity. Here we go. There you go.